39,000 years ago, in southern Italy, something strange was happening to the sky. The day began normally. By afternoon, the horizon had faded behind a thin gray haze. The light looked wrong. The birds had gone quiet. There was a faint chemical sting in the air that no human in Europe had ever experienced before. The world was still intact, but above it, something irreversible had already begun. The people standing on those hillsides had no way of knowing they were witnessing the opening hours of the largest volcanic eruption Europe would see for the next 200,000 years. An ash cloud was already climbing into the sky, spreading across the continent faster than anything alive could outrun it. The source was a place now known as Campi Flegrei, the burning fields. The ash from this single eruption would eventually settle across thousands of kilometers. Traces of it would be preserved in the Dead Sea, in Romanian hillsides, in Mediterranean seafloor sediments, and even in Greenland ice, still identifiable nearly 40,000 years later. At the time, two human species shared Europe. Both hunted the same animals. Both occupied the same shrinking landscapes at the edge of an ice age. After this eruption, only one of them remained, and the volcano responsible never truly went away. Sitting on the western outskirts of what is now Naples, the ground above Campi Flegrei has been rising for nearly 20 years. More than a meter of uplift has already been recorded. Millions of people now live across and around that same volcanic system that produced one of the most powerful eruptions in human history. Invisible from the surface, most people pass above it every day without thinking about what is underneath. Today, we're traveling back in time to that morning when the burning fields earned their name. But before we do, let me know in the comments. Where are you listening from today? And what is the time over there? I love seeing how far across the world these stories reach. Now, let's begin. Look at a map of the Bay of Naples, and the shape does not immediately reveal itself. The coastline curves around harbors and neighborhoods. The sea fills familiar spaces, and the land appears settled into its modern form. Only after tracing the contours more carefully does a larger geometry emerge, one measured not by what rises above the horizon, but by what once fell inward. Many volcanoes announce themselves through elevation. Their slopes gather over thousands of years, building peaks that dominate the landscape around them. Campi Flegrei tells a different geological story. Its defining feature was created through collapse. At the heart of the system lies a caldera, a broad depression formed when an eruption removes such an enormous volume of magma that the rock overhead can no longer support its own weight. The surface sinks into the emptied space, leaving behind a scar whose size reflects the scale of the event that produced it. Campi Flegrei's caldera extends roughly 13 kilometers, which is about 8 miles across. That distance is comparable to crossing a major city from one side to the other. Its shape is not fully visible from land because much of the structure occupies the Gulf of Pozzuoli. The western portion rests beneath the water, making the caldera part landscape and part seafloor. A traveler standing on the coast sees only fragments of the whole system, while the larger outline remains spread across both earth and sea. Along its eastern margin sits Naples. Streets, homes, ports, and public squares occupy terrain connected directly to the rim of the caldera. Millions of footsteps pass across ground shaped by volcanic processes that began long before any settlement existed here. The city and the volcanic system share the same geography, woven together so completely that separating one from the other becomes difficult. Inside the caldera is an entire district of volcanic features. More than 40 vents, craters, fumaroles, and hydrothermal areas are scattered across the landscape. Some release heated gases, others mark the locations of previous eruptions. Mineral rich waters circulate through fractures in the rock, carrying heat upward from depth. Each feature belongs to a larger network linked by the same source below. Campi Flegrei is therefore better understood as a volcanic field than as a single volcano. That source lies relatively close to the surface. Researchers estimate that the principal magma reservoir sits approximately 4 kilometers underground, which is about 2.5 miles. For a system of this size, that depth is comparatively shallow. Changes occurring within the reservoir can therefore influence the land above in ways that remain measurable over human lifetimes. Evidence of volcanic activity here reaches back at least 47,000 years. The famous eruption that transformed Europe occurred much later, meaning the system had already spent thousands of years evolving, accumulating magma, and reshaping the crust beneath southern Italy, 9 kilometers to the east, which is about 5.6 miles, stands Mount Vesuvius. Its profile is familiar throughout the world because of Pompeii. Campi Flegrei occupies a different category of volcanology altogether. It is older, broader, more intricate, and built from interconnected structures spread across an entire region. The mountain draws the eye. The caldera reshapes the land itself. Across Europe, footprints rarely lasted more than a few days. A passing herd erased them. Fresh snow covered them. Rain softened them back into soil. Human lives moved through the landscape in much the same way, leaving brief traces across a continent already being reshaped by a changing climate. 39,000 years ago, the last ice age was tightening its grip. Glaciers expanded across northern regions, and colder conditions pushed ecosystems southward. Sea levels stood roughly 80 meters lower than today, opening expanses of land that no longer exist. The floor of the modern North Sea formed a broad plain connecting territories now separated by water. Areas of the English Channel were dry as well, creating routes that animals and people could cross on foot. Europe possessed a different geography, one built around ice, grasslands, and shifting ecological boundaries. Forests occupied fewer regions than they do today. Much of the continent consisted of open steppe and tundra, stretching beneath skies that carried long winters and short growing seasons. Plant communities were compressed towards southern latitudes as advancing cold narrowed the range of habitats available to them. Each movement of climate altered the distribution of animals, and every animal migration reshaped the opportunities available to human hunters. Two human species shared this world. Neanderthals had occupied Europe for at least 400,000 years. Their history was deeply woven into the continent's climatic cycles. Generations had adapted to cold environments, developing ways of life suited to landscapes that alternated between harsh and harsher still. Stone tools, hunting strategies, and social traditions connected them to territories their ancestors had known for hundreds of millennia. A newer arrival was spreading through the same regions. Homo sapiens, anatomically modern humans whose origins lay farther southeast, had entered Europe and were gradually extending their range westward. Their camps appeared in valleys, river corridors, and plains already familiar to Neanderthal groups. The continent had become a place where two forms of humanity encountered the same mountains, crossed the same rivers, and pursued many of the same animals. Neither species existed in large numbers. Population estimates suggest that all hominins living across Europe totaled only tens of thousands. Communities were dispersed across enormous territories, often separated by distances that could take days or weeks to travel. A single band might spend months moving through a familiar circuit of hunting grounds before encountering another group. Their lives depended heavily on large animals, Mammoths grazed across open grasslands. Woolly rhinoceroses moved through colder regions. Giant deer carried antlers wider than many doorways today. Cave bears occupied sheltered areas where resources allowed them to thrive. These creatures formed part of an interconnected ecological network supporting both human species. The archaeological record preserves fragments of that arrangement. Neanderthal sites become increasingly concentrated in Western and Southern Europe, including areas of present day France, Iberia, and Croatia. Early modern human sites appear farther east and across parts of Central Europe and the Eastern Mediterranean. The distribution suggests movement, pressure, and gradual change unfolding across generations. At the same time, human culture itself was shifting. New tool traditions emerged. Symbolic objects appeared more frequently. Methods of communication, cooperation, and social organization were evolving. Archaeologists refer to this period as the transition from the Middle Paleolithic to the Upper Paleolithic, a threshold already transforming Europe before geology entered the story. Deep within a crystal no larger than a fingernail, time can remain preserved for tens of thousands of years. Long after an eruption has scattered ash across continents and buried landscapes beneath layers of volcanic debris, the crystal still carries a record of the final changes that unfolded inside the magma from which it grew. Researchers studying the Campanian Ignimbrite eruption have turned to sanidine crystals recovered from eruption deposits. These crystals formed within the magma chamber before the eruption and retained delicate chemical patterns as they developed. Using a technique known as barium diffusion chronometry, scientists can examine how chemical elements moved through the crystal structure over time. The process functions almost like reading rings within a tree, except the story being reconstructed is one of heat, pressure, and molten rock. The results reveal a surprisingly recent sequence of events. The final recharge and mixing episodes inside the magma system appear to have occurred less than 60 years before the eruption. Some estimates suggest intervals measured in years, or even months. Geological processes often unfold across spans difficult for humans to imagine, yet these findings place critical changes within a time frame that could fit inside a single lifetime. People living in southern Italy during those decades would have occupied the landscape while the system was already approaching a new state. The source of that transformation lay deeper within the earth. Fresh magma rose from the mantle and entered an existing reservoir that had spent long periods evolving underground. The newcomer carried greater heat and larger quantities of dissolved gases. As it intruded into cooler magma already occupying the chamber, the two began to mix. Temperatures shifted, chemical compositions changed, and the balance that had existed for centuries became increasingly unstable. Such mixing is important because magma behaves differently depending on its composition. The magma beneath Campi Flegrei belonged primarily to trachytic and phonolithic varieties, both rich in silica and unusually viscous. Thick magma resists flow, gas bubbles attempting to escape encounter difficulty moving through it. Water vapor, carbon dioxide, and sulfur dioxide remain trapped within the molten material, accumulating pressure as conditions evolve. One might picture a vessel being filled while its lid grows heavier at the same time. The volume of gas increases, pathways for release remain restricted, and the internal force continues building. Each pulse of fresh magma contributes additional energy to the system. Stability becomes harder to maintain as the chamber approaches critical conditions. The landscape above likely reflected these changes. Ground surfaces may have risen and fallen as magma migrated below. Hydrothermal areas could have become more active, releasing larger volumes of heated gas. Earthquakes probably rattled portions of the region as rock adjusted to changing pressures. No instruments existed to measure these signals. No seismographs traced the movement of fractures. No satellites observed deformation from above. Human communities were present, however. Small bands moved through valleys, coastlines, and hunting grounds spread across southern Europe. If tremors disturbed the earth beneath their feet, they would have noticed. If sulfur odors became stronger around geothermal areas, they would have noticed that as well. Their observations would have remained local and immediate, fragments of experience without a broader framework. Far below those wandering groups, magma continued its gradual reorganization, crystal by crystal, year by year, carrying the system toward a threshold written into the chemistry of the rock itself. There are moments in geology when energy accumulated over centuries finds a path to the surface all at once. When the Campanian Ignimbrite eruption began approximately 39,280 years ago, with an uncertainty of roughly 110 years, the first stage unfolded as a towering structure of ash, gas, and fragmented rock rising into the sky with extraordinary force. Volcanologists describe this phase as a Plinian eruption column, a term derived from Pliny the Younger, whose written observations of Mount Vesuvius preserved one of history's earliest detailed accounts of explosive volcanism. In such eruptions, dissolved gases escape from magma with explosive intensity. The rapid decompression shatters molten rock into countless fragments and propels them upward in a sustained jet. Hot gases provide lift, carrying ash and volcanic debris high above the vent for hours or even days. At Campi Flegrei, that column climbed to an estimated height of 44 kilometers, which is about 27 miles. The plume rose beyond the tropopause and deep into the stratosphere, entering a region of the atmosphere largely separated from the weather systems operating closer to Earth's surface. Rain clouds, winds, and storms that shape daily conditions remained far below the highest part of the eruption column. Reaching such an altitude transformed the event from a regional disaster into something much larger. Material injected into the stratosphere can travel immense distances before returning to the ground. Air currents at those elevations operate on continental scales, transporting volcanic particles across seas, mountain ranges, and entire climatic zones. Ash released during those first hours began a journey that would continue for months, and in some cases, years. The prevailing circulation carried much of the material eastward and southward. Fine ash and lapilli drifted across the Balkans, spread over the eastern Mediterranean, crossed the Aegean Sea, and extended into North Africa. Communities living hundreds of kilometers away, which is about hundreds of miles away, had no view of the vent itself, yet particles from the eruption still arrived from the sky. Layers of volcanic glass settled onto landscapes that had never experienced anything comparable. Sound accompanied the expanding column. The eruption generated continuous acoustic energy on a scale difficult to imagine today. Across large portions of Europe, people would have heard prolonged thunder like reverberations carrying through the atmosphere. The source remained distant, yet the sound persisted hour after hour, arriving from a horizon that offered little explanation. For human populations accustomed to storms, animal calls, and seasonal winds, this was something entirely different. As ash descended, it began preserving a record of the eruption's earliest stage. Each grain contained information about the magma from which it originated. The chemical composition of the volcanic glass was distinctive, shaped by the unique characteristics of Campi Flegrei's trachytic system. Thousands of years later, scientists examining sediment cores from across the Mediterranean can still identify these deposits by that chemical fingerprint alone. The column remains suspended above the landscape, like a connection between Earth's interior and the upper atmosphere, feeding ash into distant air currents, while the eruption continued below, writing its signature across regions far beyond the coast where it began. A towering eruption column appears powerful, yet its existence depends on balance. For hours, perhaps longer, ash and gas can continue climbing skyward as long as rising material remains buoyant enough to support its own ascent. Eventually, that balance can fail. When it does, gravity reclaims what the eruption has lifted. As the Campanian Ignimbrite eruption intensified, the volume of material entering the atmosphere grew immense. The column relied on a continuous supply of heated air, drawn inward and upward from its surroundings. That process maintained the lift necessary to keep volcanic fragments suspended. There comes a point, however, when an eruption can feed material into the column faster than the atmosphere can support it. The structure begins to destabilize, sections lose buoyancy, the upper portions descend, then the collapse spreads through the column itself. What follows is among the most destructive phenomena known in geology. Volcanologists call these events pyroclastic density currents. They are mixtures of volcanic gas, ash, pumice, and fragmented rock moving together as a turbulent mass across the surface of the Earth. Although the word flow is often used, their behavior differs greatly from lava. They surge forward with extraordinary speed, following valleys, crossing plains, and sweeping across obstacles that would halt many other geological processes. Estimates suggest that some pyroclastic density currents can travel between 100 kilometers per hour, which is about 62 miles per hour, and 700 kilometers per hour, which is about 435 miles per hour. Temperatures may range from 300 degrees Celsius or 572 degrees Fahrenheit to 700 degrees Celsius or 1292 degrees Fahrenheit. Within such conditions, survival becomes effectively impossible for anything caught directly in their path. One of their most dangerous characteristics is the way they move through the landscape. Sound does not always provide useful warning. The current itself can advance with such speed that those nearby may have little indication of its arrival before it reaches them. The combination of heat, impact, ash, inhalation, and force acts simultaneously. The Campanian Ignimbrite currents expanded outward from the source region in every direction. Their movement was not confined to valleys surrounding the eruption center. Geological evidence shows that they continued across the coastline and onto open water. The Bay of Naples offered no meaningful barrier. The currents skimmed across the sea surface, carried by momentum, heat, and density differences that allowed them to maintain forward motion far beyond the shore. Their reach extended into elevated terrain as well. On the Sorrento Peninsula, deposits indicate that these currents overtopped ridges more than 1,000 meters high. Height alone could not guarantee safety within the immediate region surrounding the eruption. Material surged across landscapes that might otherwise appear protected by topography. Forests disappeared beneath waves of ash and gas. Animal populations occupying nearby habitats vanished within moments. Vegetation, soil surfaces, and existing landforms became buried beneath newly emplaced volcanic deposits. The eruption was reshaping geography as it advanced. Today, those deposits remain spread across large areas of Campania and the adjacent seafloor. Layer upon layer of volcanic material records the passage of currents that originated from a collapsing column and transformed an eruption in the atmosphere into a sweeping event across the ground itself. Rock often appears permanent, as though it has always existed in its present form. A cliff face seems fixed, a building stone appears timeless. Yet some rocks began as events, frozen moments of extraordinary change that solidified into something future generations could touch with their hands. When the pyroclastic density currents of the Campanian Ignimbrite eruption finally lost momentum, they left behind enormous quantities of volcanic material. Ash settled among larger fragments of pumice and broken rock, layer upon layer, accumulated across the landscape, still carrying tremendous heat from its violent journey outward. The deposits did not cool immediately. Instead, they remained hot enough for physical transformation to continue long after movement had ceased. Weight pressed downward from above, while heat persisted within the deposit. Volcanic particles compacted together. In many places, fragments softened and fused at their points of contact. Individual grains gradually became part of a single mass. Through this process, loose debris was converted into a solid rock known as ignimbrite. The name preserves a memory of its origin. Derived from Latin roots associated with fire and rain, ignimbrite can be understood as fire rain turned to stone. The phrase captures a remarkable transition. Material that once traveled through the air as ash and scorching debris eventually became part of the Earth's crust, transformed from motion into permanence. Across Campania today, that history remains visible. Gray exposures appear in road cuts, coastal cliffs, and excavated hillsides. Geologists recognize these outcrops as remnants of the eruption deposit itself. What may appear to be ordinary stone is actually the preserved footprint of a volcanic catastrophe. Every layer contains information about conditions during emplacement, including temperature, flow behavior, and the sequence in which material arrived. In the Naples region, another volcanic rock often attracts more attention. Many historic structures were constructed from Neapolitan yellow tuff, a pale stone produced by a later eruption approximately 15,000 years after the Campanian Ignimbrite event. Churches, walls, and foundations display its distinctive color throughout the area. Yet beneath those younger deposits lies the older ignimbrite layer, forming part of the geological foundation upon which the modern landscape developed. Its thickness varies considerably. Near the eruption source, ignimbrite deposits can reach many meters in depth. Farther away, the layer may become comparatively thin while remaining continuous across great distances. Even where reduced to a narrow horizon within sediments, it still preserves evidence of the same moment in geological time. That continuity has made the Campanian Ignimbrite one of the most valuable marker layers in Mediterranean science. Researchers studying ancient climates, ecosystems, and archaeological sites often encounter the deposit in different locations. Because it originated from a single eruption, the layer provides a shared reference point linking records that might otherwise remain difficult to compare. A sediment core from one region and an archaeological excavation from another can be connected through the presence of the same volcanic horizon. Examining the deposit is somewhat like reading a story in reverse order. Lower layers record material that fell from the eruption column during its earlier stages. Above them lie deposits produced by successive pyroclastic currents. Finer ash settled afterward from the turbulent cloud lingering overhead. Each layer preserves part of the sequence, allowing scientists to reconstruct events from stone that once moved across the landscape as heat, ash, and fire rain. Far above the devastation unfolding across southern Italy, Another process was expanding across the sky. While pyroclastic density currents spread outward along the ground, immense quantities of fine volcanic material were being carried upward again through turbulence generated by the collapsing eruption system. This secondary plume, known as a coignimbrite ash cloud, rose into the atmosphere and began a journey that would extend far beyond the reach of the flows themselves. Unlike the dense currents that followed valleys and coastlines, volcanic ash at altitude became part of larger atmospheric circulation patterns. Winds transported microscopic fragments across enormous distances, scattering material over much of Europe and Western Asia. The eruption was no longer a regional event. It had entered the domain of continental geography. Scientists have reconstructed this dispersal through decades of fieldwork. Ash from the Campanian Ignimbrite eruption has been identified at more than 115 locations, stretching across thousands of kilometers. Researchers combined those discoveries with three-dimensional atmospheric simulations, allowing them to trace the movement of the plume through the skies of the late Pleistocene world. The resulting picture reveals an eruption whose influence reached across approximately 3,700,000 square kilometers, an area larger than modern India. The total volume of dispersed ash is estimated at between 250 and 300 cubic kilometers. Much of this material consisted of particles so fine that they remained suspended for extended periods before settling. Some drifted eastward across the Balkans and beyond. Other portions entered broader circulation systems that carried volcanic glass across regions far removed from the eruption source. Evidence of that journey continues to emerge from unexpected places. Ash attributed to the Campanian Ignimbrite has been identified on the Russian plains, more than 2,200 kilometers from Naples, which is about 1,367 miles. At such distances, the eruption itself would have been invisible, yet the atmosphere delivered its signature across the continent all the same. Another record surfaced within sediment cores extracted from the Dead Sea during drilling operations conducted in 2011. There, within finely layered deposits accumulated over tens of thousands of years, researchers identified volcanic particles whose chemical composition matched Campi Flegrei. The ash had settled onto the lake's surface approximately 39,000 years earlier and remained preserved within the sedimentary archive ever since. Traces have also been discovered in Greenland ice cores. Embedded within layers of ancient ice are tiny fragments of volcanic glass linked to the eruption. Those particles likely fell into snow somewhere across the North Atlantic region before becoming buried beneath successive years of accumulation. Through time, snow transformed into ice, preserving a distant memory of an eruption that occurred far to the south. Field studies in Romania added another piece to the story. Investigators examining lowest deposits, wind-blown sediments that accumulated across steppe environments, encountered Campanian Ignimbrite ash in greater thickness than expected. The findings suggested that earlier dispersal models may have underestimated the eruption's influence across Eastern Europe. The ash carried more than rock fragments. Fluorine compounds adhered to volcanic particles and entered soils and water after deposition. As rainfall interacted with the ash, chemical leachates spread into grazing areas and freshwater sources. Plants absorbed the contamination. Animals encountered it through food and drinking water. Long after the skies cleared, the eruption remained present across the landscape through chemistry, extending its influence across months and years in places separated by entire continents from the volcanic source. Nothing in the landscape revealed the most far-reaching consequence of the eruption. Forests could be buried, rivers could be choked with ash, entire regions could be reshaped by falling debris. Yet the process that carried the greatest climatic influence unfolded high above the world, beyond the reach of any human eye living 39,000 years ago. The eruption column that rose approximately 44 kilometers into the atmosphere, which is about 27.3 miles, delivered enormous quantities of sulfur dioxide into the stratosphere. At that altitude, volcanic gases entered a part of the atmosphere largely isolated from ordinary weather. Rain could not quickly wash them away. Winds could distribute them across immense distances. The sulfur dioxide began a chemical transformation that would extend the eruption's effects far beyond the Mediterranean basin. Within the stratosphere, sulfur dioxide reacted with water vapor. The result was the formation of sulfate aerosol droplets, particles so small that an individual droplet would escape notice entirely. Together, however, countless trillions of these droplets formed a planetary veil. Suspended high above the surface, they surrounded large portions of the northern hemisphere and altered the balance between incoming sunlight and Earth itself. Sunlight that would ordinarily have reached the ground encountered this reflective layer first. A fraction of that energy was redirected back into space. The mechanism is known as volcanic forcing, one of the most powerful natural climate drivers in the geological record. Unlike changes unfolding over thousands of years, volcanic forcing can alter temperatures within months, creating environmental shifts on timescales relevant to individual lifetimes. Computer simulations reconstructing the Campanian Ignimbrite eruption suggest substantial cooling across Europe. Regions where human populations were concentrated appear to have experienced average temperature declines between 3 degrees Celsius or 37 degrees Fahrenheit and 5 degrees Celsius or 41 degrees Fahrenheit. Across portions of Eastern Europe and the Russian plains, some models estimate cooling approaching 9 degrees Celsius or 48 degrees Fahrenheit. Those numbers may appear modest beside the temperature swings associated with full glacial cycles, yet ecosystems respond intensely to changes of this magnitude when they occur rapidly. A decline of 3 degrees Celsius or 37 degrees Fahrenheit sustained through a growing season can shorten the period available for plant growth, reduce seed production, alter flowering cycles, and diminish the abundance of grazing vegetation. Herbivores encounter poorer feeding conditions. Predators encounter fewer opportunities. Ecological pressures accumulate through entire food webs. The atmosphere itself would have appeared different. This was not a world plunged into permanent darkness. Daylight still arrived each morning. Shadows still crossed the ground. What changed was the character of the light. The sky likely took on a muted appearance as sunlight filtered through layers of sulfate aerosols overhead. Warmth reaching the surface declined. Seasonal transitions became less predictable. Living communities that had adapted to familiar environmental rhythms faced conditions outside their recent experience. Current estimates suggest the densest portion of the aerosol veil persisted for roughly 1 to 3 years before atmospheric circulation and gradual removal processes reduced its influence. Temperatures eventually recovered as the stratosphere cleared. Ecological systems, however, operated on longer schedules. Plant communities required time to reestablish themselves. Animal populations needed generations to rebound from losses. Across Europe, the climatic aftermath lingered long after the volcanic haze had faded from the sky. While volcanic aerosols spread through the atmosphere, another force was reshaping climate from the ocean below. The Campanian Ignimbrite eruption occurred at the beginning of Heinrich Event 4, one of the most severe cold episodes of the entire last glacial period. Europe was already entering a time of environmental stress when the eruption added a second layer of disruption. Heinrich events occur when immense numbers of icebergs break away from continental ice sheets and drift into the North Atlantic Ocean. During Heinrich Event 4, those icebergs originated from the Laurentide ice sheet in North America. As they traveled southward and melted, they released extraordinary amounts of fresh water into the sea. The ice also carried rock and sediment that later settled onto the ocean floor, preserving evidence of the event for future scientists to discover. That influx of fresh water affected a climate system far larger than the icebergs themselves. The Atlantic meridional overturning circulation transports heat from tropical regions toward higher latitudes. Warm surface water moves northward, releases energy into the atmosphere, then cools and sinks. This process helps maintain the climate of Europe and forms one of the most important components of Earth's heat distribution network. Fresh water interferes with this circulation because it is less dense than salty seawater. When enough fresh water enters the North Atlantic, sinking becomes less efficient. Ocean circulation weakens, and less heat reaches northern regions. Temperatures fall across large areas, even without any volcanic influence. For many years, scientists debated the relationship between Heinrich Event 4 and the Campanian Ignimbrite eruption. Determining exact ages for events nearly 40,000 years old is difficult, and early estimates left room for uncertainty. Improved dating techniques eventually provided a clearer picture. Research published in 2017 showed that the eruption occurred at the onset of Heinrich Event 4. The timing placed both events within the same critical interval. This overlap transformed a major eruption into part of a larger climatic crisis. Sulfate aerosols from Campi Flegrei reflected sunlight back into space and reduced the energy reaching the surface. At the same time, weakened ocean circulation limited the delivery of warmth into Europe. One process cooled the atmosphere from above, the other reduced heat transport through the oceans. Researchers describe the interaction as a positive feedback. Volcanic cooling may have further weakened already stressed circulation patterns. Reduced circulation then reinforced the cooling initiated by the eruption. Each process amplified the effects of the other, producing environmental changes greater than either could achieve alone. Climate reconstructions suggest that parts of Eastern Europe and the Russian plains experienced temperatures approaching some of the coldest conditions of the entire Ice Age. More significant than the absolute temperatures was the speed at which those conditions developed. Geological evidence indicates that substantial climatic deterioration occurred within years rather than over many centuries. For large mammals living across Europe, survival depended on productive landscapes and predictable seasonal cycles. Cooling shortened growing seasons and reduced plant productivity. Herbivore populations faced increasing pressure as food resources declined. Predators encountered fewer opportunities as prey became scarcer. Human populations and Neanderthal communities depended on those same ecological systems. Their numbers were already small, scattered across enormous territories. As the atmosphere dimmed and the climate cooled, the resources supporting life became less dependable. The eruption and Heinrich Event 4 arrived together, creating a rare convergence of environmental pressures across Ice Age Europe. A long history can create the illusion of permanence. For roughly 400,000 years, Neanderthals endured the shifting moods of Ice Age Europe. They lived through advancing glaciers and retreating ice, changing coastlines, and transformations in the animal communities they hunted. Generation after generation adapted to conditions that would have challenged any large mammal. Their stories stretched across spans of time so immense that it could seem inseparable from the continent itself. Yet, by about 39,000 years ago, the map of that story had grown smaller. Archaeological evidence shows Neanderthal populations increasingly concentrated in western and southern regions of Europe. Across central and eastern areas, anatomically modern humans were expanding into territories that Neanderthals had occupied for countless generations. The change did not occur in a single wave. It unfolded unevenly, with different populations moving, meeting, and competing across landscapes already shaped by climatic instability. Genetic research offers another glimpse into their circumstances. Studies of Neanderthal deoxyribonucleic acid suggest effective population sizes numbering only in the low thousands. In practical terms, the entire breeding population of Neanderthals across Europe may have been smaller than that of a medium-sized modern town. Such numbers matter because small populations are vulnerable to disruption. The loss of a hunting territory, a sequence of poor seasons, or the disappearance of a key animal species can ripple through a community with unusual force. Evidence from the final known Neanderthal sites deepens that picture. Many of the youngest sites are found in places such as Iberia and southern France, regions that served as refuges during difficult climatic periods. These were landscapes where survival remained possible while harsher conditions spread elsewhere. They represented the remaining strongholds of a people whose geographic range had steadily contracted over thousands of years. Into this setting arrived the environmental upheaval associated with the Campanian Ignimbrite eruption and the onset of Heinrich Event 4. Climate simulations indicate that the most severe cooling occurred east of the principal Neanderthal refuges. Even so, Western Europe experienced substantial temperature declines. A reduction of 3 to 5 degrees Celsius, or 37 to 41 degrees Fahrenheit, sustained across seasons could alter vegetation, reduce prey abundance, and reshape migration routes. For scattered bands already living close to ecological limits, such changes carried consequences far beyond the thermometer. The animals Neanderthals depended upon were part of interconnected food webs. Herd movements influenced hunting success. Plant productivity influenced herd movements. Climate influenced them both. When cooling shortened growing seasons and disturbed established ecological patterns, the effects traveled through the landscape in ways that no human group could fully control. Small populations possessed fewer opportunities to recover from repeated losses. Researchers remained careful when discussing the extinction of Neanderthals. The evidence does not support a single cause. Competition with modern humans, demographic pressures, genetic isolation, and environmental instability all formed part of a larger story. Within that context, the Campanian Ignimbrite eruption appears less as a lone executioner and more as an additional burden placed upon a population already carrying many others. As researcher Benjamin Black has suggested in Substance, ecosystems and societies are complicated, and when a group stands near a threshold, even one further shock can alter the outcome. The edge may already have been close. The eruption may have nudged it nearer still. Archaeological layers can sometimes read like interrupted conversations. A community leaves behind hearths, tools, ornaments, and traces of daily life. Then, without warning, the record stops. Across parts of Eastern Europe, the Balkans, and the Eastern Mediterranean, researchers have identified sites where human occupation appears to end immediately above the Campanian Ignimbrite ash layer. The people who lived there did not vanish from history entirely, yet their presence in those places came to an abrupt close, marked by a thin geological boundary that settled from the sky. The effects of the eruption extended far beyond the regions closest to Campi Flegrei. Ash fall, environmental disruption, poisoned water sources, altered migration routes, and colder conditions reached populations scattered across thousands of kilometers. Human groups living through this period faced challenges that unfolded across entire landscapes. Hunting territories changed. Familiar resources became less predictable. Routes that had connected seasonal camps may have become difficult or impossible to use for a time. The eruption touched societies already navigating the climatic instability of the late Ice Age. Its timing is especially striking because it coincides with the Middle to Upper Paleolithic transition, one of the most significant cultural transformations in prehistoric Europe. Archaeologists have long debated why new tool traditions, symbolic practices, and social behaviors appeared and spread during this period. In several regional sequences, the Campanian Ignimbrite ash layer sits directly within this transition. The relationship does not prove that the eruption caused every cultural change that followed, yet it suggests that environmental disruption may have accelerated processes already underway. Some researchers have proposed that the eruption reshaped the balance between Neanderthals and anatomically modern humans. Small Neanderthal populations were concentrated in refuges that may have been especially vulnerable to ecological stress. If the eruption reduced those populations further, recovery would have become increasingly difficult. Territories once occupied by Neanderthal groups could then have been recolonized by expanding populations of modern humans as environmental conditions gradually improved. What stands out most clearly is that modern humans endured the crisis and eventually expanded. The populations that returned to affected regions after the volcanic winter were not necessarily identical to those who had occupied them before. Archaeological evidence points toward changing technologies, shifting patterns of social organization, and new approaches to survival. Networks connecting distant groups may have become increasingly important. Information, materials, and innovations could move across broader areas, helping communities adapt to changing circumstances. Genetic evidence offers another perspective. Studies of living human populations indicate that all modern humans outside Africa descend from a comparatively small ancestral population. Researchers describe this pattern as a population bottleneck, a period when human numbers were greatly reduced before later expansion. The precise causes and timing remain subjects of ongoing investigation, yet the Campanian Ignimbrite eruption falls within a period that continues to attract attention from geneticists examining these demographic shifts. Seen across the sweep of human history, the contrast is profound. One human species entered this period already under pressure and soon disappeared. Another endured the same catastrophe and ultimately spread across the continent. The reasons were complex, involving climate, population size, adaptability, social networks, and chance. Among those forces stood a supervolcanic eruption whose influence stretched from geology into biology, leaving its imprint on the story of who remained when the skies finally cleared. A footprint in fresh snow disappears quickly when it stands alone. A trail made by many travelers lasts longer, reinforced by each new passage. Across Ice Age Europe, two human species faced the same environmental crisis, yet their paths diverged. The reasons remain the subject of ongoing research, but several patterns emerge repeatedly from archaeological, genetic, and ecological evidence. One of the most important differences may have been the scale of social connections. Archaeological sites associated with anatomically modern humans reveal materials that traveled astonishing distances. Marine shells appear far inland. Particular stone types are found hundreds of kilometers from their geological source. A stone transported 300 kilometers, which is about 186 miles, represents more than movement across a landscape. It points to relationships linking communities separated by great distances. Goods, ideas, and people appear to have moved through networks extending far beyond a single valley or hunting territory. Neanderthal communities also exchanged materials, yet the evidence generally suggests more localized patterns. Resources tended to remain closer to their origins, indicating smaller spheres of interaction. Such networks function effectively during stable periods, but widespread environmental disruption changes the equation. When familiar resources vanish, a population connected to distant groups gains access to knowledge and opportunities beyond its immediate surroundings. Technology may have played a related role. During and after this period, modern human toolkits became increasingly diverse. Archaeological assemblages reveal growing specialization, with different tools designed for different tasks and environments. Flexibility matters during ecological upheaval because conditions can shift faster than traditions. Communities capable of experimenting, adapting, and spreading successful innovations may gain advantages that accumulate over generations. Information itself may have been among the most valuable resources available. A larger social network allows discoveries made in one region to benefit people living elsewhere. Knowledge of migration routes, edible plants, seasonal resources, or safer territories can move from group to group. Information travels across landscapes far more rapidly than individuals exploring alone. In difficult periods, that flow of knowledge can reduce uncertainty and improve survival prospects. Population structure also deserves attention. Even if modern human groups suffered severe losses from climatic deterioration, volcanic effects, and ecological collapse, their broader distribution created a demographic buffer. Separate communities, spread across different regions, increased the likelihood that some populations would endure local disasters. Survivors could reconnect, exchange mates, share resources, and rebuild. Small, isolated populations face a different challenge. If numbers fall too low, recovery becomes increasingly difficult even when environmental conditions improve. This distinction should not be mistaken for a measure of intelligence. Evidence gathered over decades has transformed scientific understanding of Neanderthals. They crafted sophisticated tools, cared for injured individuals, created symbolic objects, and buried their dead. Their cognitive abilities were substantial and complex. The disappearance of Neanderthals cannot be explained by any simple notion of intellectual inferiority. Viewed through the lens of network science, the contrast appears less personal and more structural. Catastrophes test connections as much as individuals. A population linked across broad territories possesses multiple pathways through which people, resources, and ideas can move. A fragmented population has fewer alternatives when those pathways fail. As Europe emerged from volcanic winter and climatic instability, modern humans retained enough connections to rebuild. Neanderthals, already reduced to scattered refuges, may have found those connections growing too thin to sustain recovery. In that sense, survival may have depended less on who people were and more on how they were connected. Across the scar left by the Campanian Ignimbrite, time resumed its patient work. Slopes weathered, streams carved fresh paths through volcanic deposits. Plant communities gradually reclaimed ground, that had once been buried beneath heat and ash. For roughly 25,000 years, the caldera entered a period of relative calm. Generations of animals lived and disappeared. Human populations moved across changing landscapes. The climate itself shifted as the great ice sheets of the last glacial period slowly retreated and sea levels began their long rise. From the surface, the volcanic system appeared subdued. Deep underground, however, magma continued to gather, cool, evolve, and migrate through a complex network of reservoirs and fractures. Campi Flegrei had not reached the end of its story. The forces responsible for one of the largest eruptions in European history remained active within the crust, reshaping the region in ways that could not yet be seen. Approximately 15,000 years ago, during the climatic transition that would eventually lead toward the present interglacial world, the system reawakened. A new eruption began. It was smaller than the Campanian Ignimbrite, yet still immense by any human standard. Modern volcanologists classify it as a volcanic explosivity index 6 event. More than 40 cubic kilometers, which is about 9.6 cubic miles, of volcanic material were expelled into the surrounding landscape and atmosphere. The eruption produced what geologists now call the Neapolitan yellow tuff. Its name comes from the distinctive pale yellow color of the rock formed from compacted volcanic deposits. Layers of ash, pumice, and fragmented stone accumulated, settled, and hardened into a material that would remain visible for thousands of years. Even today, these deposits form a recognizable component of the geology surrounding the Bay of Naples. As the eruption progressed, the structure of the volcanic field changed once again. The withdrawal of magma from underground reservoirs destabilized the crust above. Portions of the surface collapsed inward, creating a second caldera nested inside the older one. This produced the unusual geometry that characterizes Campi Flegrei today, a caldera within a caldera, each collapse preserving evidence of a different chapter in the region's volcanic history. The consequences extended beyond the volcanic field itself. Shorelines shifted. Sections of the seafloor were modified by eruptive deposits and structural deformation. The shape of the Bay of Naples evolved alongside the eruption, linking geological processes beneath the ground to the broader geography of the surrounding coast. Maps of the region would look different before and after this event, even if those changes unfolded on scales far larger than any individual observer could easily perceive. The yellow stone left behind acquired a second life long after the eruption ended. Over succeeding millennia, communities quarried the durable tuff and used it as a primary building material. Walls, foundations, churches, and homes throughout the region incorporated rock born from volcanic violence. In this way, the eruption became woven into daily life, its deposits transformed into the fabric of human settlement. Following the Neapolitan yellow tuff eruption, volcanic activity entered a different phase. At least 70 smaller eruptions occurred between 15,000 and 3,800 years ago, constructing craters, cones, and volcanic lakes across the caldera. The landscape visible today emerged gradually from that sequence, shaped by many eruptions rather than a single event. A traveler approaching the Bay of Naples during the first millennium before the Common Era would have encountered a landscape that seemed to resist ordinary explanation. Hills rose where eruptions had piled volcanic debris. Circular lakes occupied ancient craters. Openings in the ground exhaled warm gases. Pools of mud stirred and released bubbles without any visible source. Across Campi Flegrei, geological processes that had been active for thousands of years remained present at the surface. shaping a world unlike any other along the Mediterranean coast. When Greek settlers established colonies in southern Italy during the 8th century before the Common Era, they entered a region already marked by this volcanic inheritance. The terrain appeared alive. Steam drifted from fissures. Sulfur scents lingered in the air. Certain patches of earth felt warm beneath bare feet. Lakes filled old explosion craters, their dark waters reflecting surrounding slopes formed by eruptions that had long since passed from memory. The landscape invited interpretation, and mythology provided a language for understanding what geology had created. Among the most influential features was Lake Avernus. Formed within a volcanic crater, the lake measured roughly half a kilometer across, which is about zero point 0.3 miles, and reached depths of approximately 33 meters. Its waters occupied a depression surrounded by steep walls, creating a setting that appeared naturally enclosed from the wider world. Volcanic gases occasionally accumulated around its margins. Ancient observers reported that birds flying through these fumes sometimes died and fell into the water, an observation that left a lasting impression on those who witnessed it. To Greek settlers, such a place seemed to occupy a threshold between familiar reality and something deeper. They named the lake Avernus, derived from a Greek term meaning birdless. The absence of birds was interpreted as evidence that the location touched a realm beyond ordinary life. Stories grew around the crater. The boundary between the living and the dead appeared unusually thin there. Over generations, Avernus became identified as an entrance to Hades, the underworld of Greek belief. Roman culture inherited these traditions and expanded them. By the 1st century before the Common Era, Campi Flegrei had become woven into some of the most influential literature of the ancient world. The poet Virgil chose this landscape as the setting for one of the central episodes of the Aeneid. In the 6th book, the hero Aeneas journeys into the underworld through a cave associated with Lake Avernus, guided by the prophetic Cumaean Sibyl. The descent unfolds through a geography shaped directly by the volcanic terrain surrounding the lake. One phrase from Virgil's account became especially famous. He described the path into the underworld with words often translated as the descent to Avernus is easy. The image endured for centuries. Readers encountered a vision of the afterlife, rooted in a real location, a volcanic landscape whose unusual features had inspired generations of storytelling. The influence did not end with Rome. More than 1,000 years later, Dante drew heavily upon Virgil while constructing the underworld of the Divine Comedy. Through that literary lineage, the crater lakes, steaming vents, and sulfurous ground of Campi Flegrei helped shape one of Western civilization's most enduring images of hell. Geological forces had sculpted the terrain, and human imagination transformed that terrain into mythology. Few places reveal the Roman character more clearly than Campi Flegrei. Here was a landscape shaped by eruptions, marked by steaming ground, crater lakes, and restless geology. Earlier cultures had filled it with stories of gods, prophecies, and journeys into the realm of the dead. The Romans inherited those stories, yet they also saw harbors, resources, trade routes, and opportunities. In Campi Flegrei, myth and engineering occupied the same terrain. The heart of Roman activity became Puteoli, known today as Pozzuoli. Positioned along a naturally favorable stretch of coastline, the city developed into one of the most important commercial centers in the empire. Before the rise of Ostia as Rome's principal harbor, grain shipments arriving from Egypt and goods transported from the eastern Mediterranean often passed through Puteoli. Merchant vessels crowded its waterfront. Warehouses stored cargo from distant provinces. The prosperity of Rome itself became linked to a port built directly within an active volcanic region. Urban development followed commercial success. Roads, markets, temples, and public buildings spread across the caldera floor. Among the most impressive structures was the Flavian Amphitheater of Pozzuoli, capable of seating approximately 20,000 spectators. It ranked as the third largest amphitheater in the Roman world. Crowds gathered there for spectacles and ceremonies, often unaware that the ground beneath them formed part of a volcanic system whose history stretched far beyond human memory. Along the nearby coast stood Baiae, a settlement that acquired a reputation for luxury throughout the empire. Wealthy families constructed villas overlooking the bay. Senators, generals, and emperors visited its shores. The attraction was not merely scenic beauty. Volcanic heat circulating through underground waters created abundant thermal springs. Warm pools and mineral-rich baths became the foundation of an elaborate culture of recreation and wellness. Historical figures became closely associated with the region. Julius Caesar owned a villa at Baiae. Augustus spent his final days nearby. Ancient sources describe Nero using the bay as a setting for celebrations and displays of imperial extravagance. Their presence reflected the prestige attached to the area, a place where nature supplied comforts that Roman engineering eagerly enhanced. The thermal waters themselves inspired particular attention. Romans believed many springs possessed healing qualities. Bath complexes were designed to capture, channel, and regulate naturally heated water emerging from the hydrothermal system below. Stone chambers, pools, tunnels, and conduits transformed volcanic energy into public infrastructure. The same geological processes capable of producing future eruptions supplied the warmth that attracted visitors from across the empire. Even Lake Avernus underwent transformation. The crater lake, once regarded as an entrance to the underworld, acquired a strategic military role during the 1st century before the Common Era. In 37 before the Common Era, the General Agrippa incorporated the lake into an ambitious naval project known as Portus Julius. Canals connected separate bodies of water. Shorelines were reshaped through engineering works. Warships trained in waters that poets continued to associate with journeys beyond death. That coexistence of practicality and imagination defined the Roman relationship with Campi Flegrei. Engineers excavated canals beside sacred landscapes. Merchants conducted business within sight of steaming hills. Naval officers organized fleets on a lake celebrated in epic poetry. The volcano remained present in every aspect of the environment, woven into commerce, politics, architecture, and daily life, its influence extending through both stone and story. Stone often gives the impression of permanence. Temples rise, roads endure, and harbors seem fixed against the sea. At Campi Flegrei, the ground itself offered a different lesson. Beneath cities, markets, and villas, the caldera continued its gradual motion, lifting and lowering the landscape through forces operating far below human sight. The process is known as bradyseism, a term derived from Greek words meaning slow and earthquake. Unlike the abrupt violence commonly associated with volcanic activity, bradyseism unfolds across decades and centuries. Magma and hydrothermal fluids shift through the crust, altering pressure within the volcanic system. As pressure increases, the caldera floor rises. When pressure diminishes, the surface settles downward again. Human lifetimes pass while these movements continue, often so gradually that each generation notices only a small part of a much larger cycle. Roman builders could not perceive the full rhythm of that motion. They established ports, warehouses, bath complexes, and luxurious residences along the shoreline, confident in the geography before them. Their structures stood atop a landscape that appeared stable. Beneath those foundations, however, the volcanic system remained active, reshaping the region at a pace measured not in days or years, but in centuries. From approximately the 4th century after the Common Era until the 15th century, Campi Flegrei entered a prolonged phase of subsidence. The caldera floor slowly descended, coastlines shifted almost imperceptibly. Areas that had once stood comfortably above sea level moved closer to the water. Harbors changed shape. Waterfront districts faced a challenge that no engineer could fully prevent, because the land supporting them was gradually sinking. Baiae experienced the transformation most dramatically. Once celebrated as one of the Roman world's most fashionable resort towns, it watched the sea advance little by little across streets and courtyards. Villas that had overlooked the bay found themselves increasingly threatened by encroaching water. Public buildings, gardens, and shoreline structures slipped beneath the surface as the centuries passed. The process lacked the spectacle of a sudden disaster. Its power came from persistence. Evidence of this movement survives in one of Campi Flegrei's most famous archaeological landmarks, the Macellum of Pozzuoli. 3 marble columns still stand there today. They were erected on dry land during the Roman period, yet their surfaces preserve a geological record. Marine mollusks bored distinctive holes into the stone when the structure sank below sea level. Those marks appear approximately 7 meters above the original ground surface, showing how deeply the site subsided before later uplift raised it once more. The columns function almost like a diary written jointly by the sea and the volcano. Modern visitors can witness an even more striking consequence beneath the waters off Baia. Divers move through submerged streets where mosaic floors remain visible. Walls outline former rooms. Statues rest where they were placed many centuries ago. The town survives in an underwater state, preserved through the same geological processes that altered its fate. Bradyseism continues today, reminding residents that Campi Flegrei remains a living volcanic system. The drowned ruins of Baiae are neither an isolated curiosity nor an unrelated archaeological accident. They are part of a continuing story, one written by a caldera whose movements have shaped landscapes, civilizations, and human memory across thousands of years. Maps can become outdated in a single human lifetime. Along the shores of Campi Flegrei, people living at the beginning of the 16th century witnessed a landscape changing shape before their eyes. Fishermen, merchants, and farmers noticed something unusual. Areas that had once been underwater were beginning to emerge. The coastline was creeping outward, revealing fresh ground where waves had recently moved. Records from the early years of the century describe this gradual uplift. By around 1502, residents near Pozzuoli could already see evidence that the caldera floor was rising. The change unfolded year after year, subtle enough to blend into daily life, yet persistent enough to attract attention. Beneath the surface, pressure was accumulating within the volcanic system, lifting the land as magma and heated fluids shifted through the crust. As the 1530s progressed, another sign appeared. Earthquakes became more frequent, tremors rattled buildings and disturbed routines. Each year brought additional shaking. What had begun as occasional disturbances developed into a pattern that communities could no longer ignore. The ground itself seemed restless. Late in September of 1538, that restlessness accelerated dramatically. On the 28th day of the month, approximately 20 separate tremors were reported between dawn and nightfall. The sequence unfolded hour after hour. People moved through streets already familiar with earthquakes, yet the intensity and frequency suggested that something larger was approaching. That evening, fractures opened near the shoreline. Water surged from the cracks. Witnesses described streams that first appeared cool and then became dangerously hot. Steam rose from newly opened vents. The familiar boundary between land and the forces below had begun to break apart. At approximately 7 in the evening, on September 29th, 1538, the eruption commenced. Magma rising through water, saturated sediments produced violent explosions. Ash, steam, fragmented rock, and volcanic debris blasted upward from the new vent. During the earliest stage, the eruption was hydromagmatic, driven by the interaction between seawater and molten material ascending from below. The activity continued through the night and into the following days. Around the vent, layers of ash and rock fragments accumulated rapidly. A cone started taking shape where no hill had existed before. Residents watched the landscape transform in real time. The process that ordinarily requires centuries of erosion and deposition unfolded within a single week. 7 days after the eruption began, a new volcanic hill stood above the coast. It reached approximately 123 meters in height. The feature became known as Monte Nuovo, meaning New Mountain. A shallow bay had been replaced by a landform visible for kilometers, which is about 6.2 miles across the surrounding region. Geography had rewritten itself within the span of a few days. Letters written by eyewitnesses preserve the event with unusual clarity. Their accounts describe trembling ground, fountains of ash, and the astonishing sight of a mountain growing from terrain they had known throughout their lives. These observations remain among the most valuable historical records of volcanic activity anywhere in the world. The eruption ended on October 6th with a final, powerful explosion. 24 people who had climbed the cone to observe the phenomenon were killed. Since that week, in 1538, Campi Flegrei has produced no eruption. The volcanic system, however, has never ceased moving beneath the surface. A volcano does not need to erupt to announce its presence. Sometimes it speaks through movement measured in centimeters, through subtle changes in the chemistry of rising gases, through patterns that emerge only when decades of observations are placed side by side. Following the birth of Monte Nuovo in 1538, Campi Flegrei entered another long chapter, one marked less by explosions than by persistent signs of activity deep below the surface. The modern phase of that story began in 1950. Instruments installed across the caldera detected renewed uplift of the ground along with a modest increase in seismic activity. At first, the changes appeared manageable. The movements were small, the earthquakes generally minor, yet volcanologists recognized that the system had shifted from relative stability into a new period of unrest. More importantly, the signals never completely disappeared afterward. As the decades passed, the caldera continued its slow rhythm of inflation and deflation. Pressure accumulated beneath the surface, lifting portions of the landscape. Later, some of that uplift would reverse as the ground settled again. Each cycle revealed that magma and hydrothermal fluids remained active within the crust, continually redistributing energy beneath towns, roads, and harbors. One of the most significant episodes occurred between 1969 and 1972. During those 3 years, the ground rose approximately 1.7 meters. Earthquake swarms accompanied the uplift, producing repeated tremors that reminded residents of the region's volcanic history. Despite the intensity of the unrest, no eruption followed. Eventually, the inflation slowed, and the caldera entered a period of subsidence. The changes were visible far beyond scientific instruments. In Pozzuoli, the harbor offered an unmistakable demonstration of the rising land. Areas that had accommodated boats with ease became progressively shallower. Vessels that once floated freely began scraping the bottom. The seafloor itself was moving upward as the caldera floor expanded beneath it. Daily commerce became a measure of geological motion. A curious pattern emerged when researchers examined multiple decades of data. Each inflation episode raised the ground substantially. Deflation followed, lowering parts of the caldera again. Yet the downward movement rarely erased all of the previous uplift. The system behaved like a staircase constructed from alternating rises and falls. Every cycle left the landscape slightly higher than before. By comparing measurements collected since 1950, scientists concluded that the caldera floor had experienced a net increase in elevation across the modern monitoring era. Campi Flegrei was not merely oscillating around a fixed position. On balance, it was rising. The cumulative effect became one of the defining characteristics of the unrest. As monitoring technology improved, researchers gained access to increasingly detailed information. Satellite observations, ground deformation surveys, earthquake records, and gas analyses revealed recurring combinations of signals. Uplift accelerated. Seismic swarms appeared. Volcanic gases changed composition. The sequence varied in intensity, yet the overall pattern remained familiar. Historical records from the Monte Nuovo eruption provided an unexpected point of comparison. Descriptions from 1538 spoke of uplift, increasing earthquakes, ground fractures, and thermal changes preceding the eruption. Modern observations displayed a family resemblance to those accounts. The similarities did not guarantee that another eruption was imminent, but they confirmed that the volcanic system responsible for Monte Nuovo remained active, continuing its long conversation with the landscape above. There are moments when a volcano appears to gather itself for an event that never arrives. Instruments record accelerating changes. Earthquakes multiply. The land shifts upward. Communities prepare for a future that seems increasingly certain. Then, at the last moment, the process stalls. Campi Flegrei entered such a moment during the early 1980s, producing the most intense volcanic crisis the region had experienced since the birth of Monte Nuovo. The episode began in November of 1982. Ground deformation, already a familiar feature of the caldera, accelerated beyond previous modern observations. Month after month, the surface continued to rise. Scientists watched benchmarks, buildings, roads, and harbor structures move upward together as pressure accumulated below. What had once appeared as gradual unrest transformed into a sustained emergency that extended through December of 1984. Across those 2 years, the ground rose approximately 1.8 meters. That increase exceeded the uplift recorded during the 1969 to 1972 crisis. Earthquake activity expanded as well. More than 16,000 earthquakes were detected during the episode. Many were small, though their sheer number created a persistent reminder that the crust beneath the caldera was adjusting to forces deep underground. Residents of Pozzuoli experienced the unrest directly. Tremors became part of daily life. Walls developed cracks. Older masonry structures showed signs of strain. Concern intensified on October 4th, 1983, when a magnitude 4 earthquake struck the area. The event was not catastrophic, yet it damaged buildings throughout the town. Ceilings collapsed in some structures, and the shaking demonstrated that the crisis had entered a more serious phase. Only days later, seismic activity escalated further. On October 13th, more than 250 earthquakes occurred within a period of roughly 5 hours. The swarm arrived with unusual intensity and heightened fears that magma might be approaching the surface. Authorities faced a difficult decision. Memories of the region's volcanic history weighed heavily on every discussion. An evacuation order followed. Approximately 40,000 residents were moved from Pozzuoli as a precaution. Streets that had been filled with ordinary routines became pathways for relocation. Families left homes uncertain of what the coming weeks might bring. Scientists, civil authorities, and local communities confronted the same unsettling possibility that they could be witnessing the immediate lead up to a new eruption. The concern was grounded in evidence. Historical descriptions from 1538 described sequences of uplift and seismic activity before Monte Nuovo emerged. The modern crisis displayed similarities that could not be dismissed. Many volcanologists concluded that magma had likely risen to relatively shallow levels beneath the caldera. Then the trajectory changed. The uplift slowed, earthquake activity gradually decreased. No eruption occurred. The crisis that had seemed to be building toward a volcanic climax instead entered a period of relaxation. Researchers now commonly describe the 1982 to 1984 event as an aborted eruption, a situation in which magma ascended through the crust but halted before reaching the surface. The precise reasons remain uncertain, reflecting the complexity of volcanic systems. Deflation followed during subsequent years. Roughly 1 meter of the earlier uplift was reversed as the ground subsided, yet the caldera did not return to its previous position. A portion of the elevation gain remained, adding another step to the long upward trend that had been developing since the middle of the 20th century. A caldera does not announce its intentions in a single dramatic moment. Its signals accumulate gradually, recorded in millimeters of uplift, faint tremors deep underground, and gases rising through fractures that connect the surface to chambers far below. Since 2005, Campi Flegrei has been delivering those signals with unusual persistence. Following a period of relative stability during the late 20th century, the ground began rising again in 2005. At first, the movement appeared modest, another pulse in a system known for cycles of inflation and deflation. Years passed, however, and the upward trend continued. Periods of acceleration alternated with slower intervals, yet the broader pattern remained unchanged. The surface kept climbing. Measurements from Rione Terra in Pozzuoli, the point experiencing the greatest deformation within the caldera, reveal the scale of that change. By late 2025, total uplift since 2005 had exceeded 148 centimeters. Roads, buildings, waterfront structures, and archaeological remains have all been carried upward by a landscape responding to forces beneath it. The movement is gradual enough to escape notice on a single day, though unmistakable when measured across decades. Seismic activity has evolved alongside the uplift. Earthquakes became more frequent after 2018, concentrating around the Solfatara and Pisciarelli sector of the caldera. Most originate at depths between 1 kilometer, which is about 0.6 miles, and 4 kilometers, which is about 2.5 miles. These depths place the activity directly beneath one of the most densely populated portions of the volcanic field. Many of the earthquakes are too small for residents to feel. Sensitive instruments detect motions far below the threshold of human perception. Since 2022, machine learning assisted seismic networks have cataloged nearly 50,000 individual events. Each tremor contributes another point to a growing map of fractures and pathways underground. Together, they reveal a crust responding continuously to pressure, fluid movement, and the transfer of heat. Larger earthquakes occasionally break through this background activity. In June 2025, the strongest event of the current unrest episode reached magnitude 4.6. The shaking was felt across Naples and neighboring communities. Older buildings sustained minor damage, and many residents were reminded that the caldera remains an active geological system rather than a relic of distant history. Gas emissions provide another line of evidence. The fumarole field at Solfatara and Piscarelli has shown elevated output of carbon dioxide. This matters because carbon dioxide can rise directly from magma at depth. Hydrothermal systems also release gases, yet increasing carbon dioxide levels often attract particular attention from volcanologists because they may reflect changes occurring deeper within the volcanic plumbing network. Authorities continue to maintain a yellow alert level, the second of four stages within Italy's volcanic warning framework. That status has remained in place since 2012. Emergency plans are active. Monitoring networks operate continuously. Scientists analyze ground deformation, seismic activity, gas chemistry, and temperature measurements, searching for patterns within a caldera that has spent nearly 2 decades rising, breathing, and reshaping itself one increment at a time. Maps often create the illusion of distance. Colored hazard zones appear as shapes on paper, bounded by neat lines and labels. Roads trace orderly paths between neighborhoods. Population figures become statistics. At Campi Flegrei, those abstractions dissolve into a reality measured in apartment blocks, schools, hospitals, ports, and the daily movements of millions of people living atop an active volcanic system. Approximately 500,000 people reside within the caldera itself. Communities such as Pozzuoli and Boccoli occupy terrain shaped by eruptions, uplift, subsidence, and hydrothermal activity extending back tens of thousands of years. Residential districts spread across slopes, crater rims, and coastal plains. Markets open each morning. Ferries cross the bay. Children walk to school above a landscape whose deeper structure remains in constant motion. Beyond the caldera boundary lies a much larger population. The greater Naples metropolitan region contains roughly 3 million people who could be affected by a significant eruption through ashfall, pyroclastic density currents, disrupted infrastructure, or secondary hazards such as mudflows. Few volcanic regions on Earth combine such geological complexity with such extraordinary population density. This setting distinguishes Campi Flegrei from many famous volcanoes. Scientists are not observing an isolated mountain rising above forests or unoccupied terrain. Monitoring stations operate among neighborhoods, roadways, industrial facilities, archaeological sites, and transportation networks. Instruments tracking deformation and seismicity share space with the routines of modern urban life. The volcano and the city occupy the same ground. Naples itself reflects that relationship. One of Europe's oldest continuously inhabited cities extends across the eastern portion of the volcanic field. Its waterfront faces the bay, shaped by earlier eruptions. Beneath streets and buildings lies volcanic stone excavated and reused over many centuries. Tunnels, cisterns, foundations, and underground chambers preserve evidence of a city constructed within a landscape created by fire and ash long before recorded history. Population alone does not define the challenge. Movement is equally important. Emergency planners must consider how hundreds of thousands of residents could leave areas of greatest risk if unrest intensified toward eruption. The highest hazard zone includes roughly 500,000 people. Relocating such a population would require coordination on a scale rarely attempted in Europe outside wartime or major natural disasters. Italy's Civil Protection Department has spent years developing and refining evacuation strategies. Transportation corridors, assembly points, regional partnerships, communication systems, and public preparedness programs form part of an extensive planning effort. The goal is to ensure that warning signs are recognized early enough for orderly movement before dangerous conditions develop. Even with detailed preparation, practical difficulties remain. Urban congestion affects daily traffic throughout the region under ordinary circumstances. During an emergency, the number of vehicles, buses, emergency services, and evacuees could place extraordinary demands on roads and transportation infrastructure. Timing becomes critical because volcanic crises do not always follow predictable schedules. For that reason, the significance of Campi Flegrei today extends beyond geology alone. It represents a meeting point between deep earth processes and modern civilization. Beneath neighborhoods, ports, hospitals, and historic districts, the caldera continues its gradual cycles of uplift and unrest, while above it, millions of lives unfold across one of the most densely inhabited volcanic landscapes on the planet. Among the many challenges posed by Campi Flegrei, one exists beyond magma chambers, fault systems, and volcanic gases. It emerges from human memory. Communities remember past warnings. They remember disruptions, evacuations, and predictions that did not culminate in eruption. Over time, those memories become part of the hazard itself. Since the middle of the 20th century, the caldera has experienced several major episodes of unrest. Activity beginning around 1950 drew scientific attention. Another significant phase unfolded between 1969 and 1972. The crisis of 1982 through 1984 prompted the evacuation of tens of thousands of residents. The current period of unrest, which began in 2005, continues today. Each episode produced uplift, earthquakes, and concern. None produced an eruption. From a scientific perspective, those events were genuine volcanic crises. The ground moved, seismic networks recorded thousands of earthquakes, gas emissions changed, deep processes were clearly affecting the surface. Yet for many residents, the most visible outcome was that daily life eventually returned to normal. Homes remained standing, neighborhoods endured. The feared eruption never arrived. This creates a dilemma known among hazard researchers as the cry wolf effect. When warnings are issued repeatedly without the anticipated disaster occurring, confidence in future warnings can gradually weaken. The process is understandable. People build expectations from experience. If several emergencies pass without catastrophe, future alerts may feel less urgent, even when evidence suggests otherwise. At Campi Flegrei, the stakes attached to that perception are unusually high. Authorities must decide whether volcanic signals justify extraordinary actions affecting hundreds of thousands of people. Evacuation orders carry enormous consequences. Businesses close, transportation systems strain under demand, families leave homes without knowing when they will return. Economic losses can be substantial, and public trust can suffer if the eruption never comes. The opposite decision carries a different burden. If officials delay action and a dangerous eruption begins, consequences could unfold far more rapidly than evacuation efforts can compensate for. Lives may depend on choices made amid uncertainty before anyone possesses complete information. The imbalance between those outcomes makes every warning decision exceptionally difficult. Geology adds another layer of complexity. Campi Flegrei does not follow a simple script. Historical evidence indicates that magma has approached the surface and then stopped. Unrest episodes can persist for years before subsiding. Ground uplift may accelerate, slow, or reverse. Earthquake swarms appear and fade. Scientists continue refining models of these processes, yet no reliable method exists for determining with certainty whether a specific crisis will end peacefully or culminate in eruption. That uncertainty means volcanology operates within probabilities rather than guarantees. Researchers evaluate patterns, compare historical episodes, analyze gas chemistry, and monitor deformation with extraordinary precision. Their observations improve understanding, though they cannot eliminate ambiguity from a living volcanic system. For residents around Naples, these questions are not theoretical. They unfold while the caldera continues to rise. Emergency planners review evacuation routes. Scientists examine new data arriving each day. Public officials weigh competing responsibilities. Above them stretches a familiar urban landscape, while below it the volcano continues its long conversation through motion, pressure, and time, offering signals whose meaning remains one of the most difficult judgments in modern hazard science. Across the slopes, roads, crater rims, and fumarole fields of Campi Flegrei, instruments now stand watch in places where earlier generations relied on observation alone. The volcano still communicates through uplift, fractures, gases, and earthquakes, yet the language is being recorded with a level of detail that would have seemed impossible only a few decades ago. One of the most important advances lies in the study of seismic activity. Every crack that forms within rock releases a pulse of energy. Many of these earthquakes are so small that people never notice them. Modern monitoring networks capture signals from thousands of sensors distributed across the caldera, collecting streams of data every second. Machine learning systems, trained to recognize earthquake signatures within enormous datasets, can now identify events far weaker than those once detectable through manual analysis. The nearly 50,000 earthquakes cataloged since 2022 would have been beyond the reach of earlier monitoring methods. Each recorded tremor adds another point to a growing map of stress and movement beneath the surface. Measurements of ground deformation provide another perspective. Global positioning system. Stations fixed to the landscape track, changes measured in millimeters. Above them, radar instruments carried by orbiting satellites repeatedly scan the same terrain. Through a technique known as interferometric synthetic aperture radar, scientists compare successive images and calculate how much the ground has shifted between observations. The result is a detailed picture of inflation and subsidence across the entire caldera. Areas rising most rapidly become visible, while neighboring regions may remain comparatively stable. Movements that would escape human perception emerge clearly when viewed through years of accumulated measurements. Gas monitoring offers insight into processes occurring deeper underground. At Solfatara and Pisciarelli, fumaroles release mixtures of volcanic gases and steam that travel upward through fractures in the crust. Instruments continuously measure emissions of carbon dioxide, sulfur dioxide, hydrogen sulfide, and water vapor. The proportions of these gases can change as temperature, pressure, and magma movement evolve below. Researchers pay close attention to those shifts because gas chemistry often reflects conditions inaccessible by any direct observation. The fumaroles function as natural sampling points, carrying information from depths that drilling cannot easily reach. Gravity measurements contribute another layer to this picture. Sensitive instruments detect tiny variations in Earth's gravitational field across the caldera. Such changes may indicate that magma, groundwater, or volcanic gases are redistributing beneath the surface. A region becoming denser exerts a slightly stronger gravitational pull. A region losing mass exerts a slightly weaker one. These differences are extraordinarily small, yet modern equipment can detect them and incorporate them into broader models of subsurface behavior. No single instrument provides a complete answer. The strength of modern volcanology comes from combining many streams of evidence into one evolving interpretation. Earthquakes reveal fracturing rock, deformation records, shifting pressure. Gas chemistry reflects changing conditions at depth. Gravity measurements trace movement of material through the volcanic system. Together, these tools create the closest view humanity has ever possessed of an active supervolcano. The picture they reveal is neither dormant nor stable. Campi Flegrei remains active, changing from year to year, a living geological system whose interior is being observed with unprecedented clarity while it continues its long and restless motion. Possibility stretches across a wide spectrum at Campi Flegrei. The same volcanic system that produced a modest cone in historical times and a continent-altering eruption in distant prehistory remains capable of outcomes that differ enormously in scale. Modern scientists do not focus on a single forecast. They study a range of scenarios, each carrying its own consequences for the millions of people who live around the Bay of Naples. At the smaller end of that range stands an event comparable to the eruption that created Monte Nuovo in the 16th century. In such a scenario, a new fracture could open somewhere within the caldera. Explosions of ash, steam, and fragmented rock might continue for days, gradually building a fresh volcanic cone where none existed before. Damage near the vent would be severe. Roads, homes, and infrastructure within the immediate area could be destroyed. Yet if warning signs developed clearly and evacuations were completed in time, the broader disaster could remain limited. Modern monitoring networks are designed with precisely this possibility in mind. Scientists also examine larger eruptions, including those classified as Volcanic Explosivity Index 4 or Volcanic Explosivity Index 5 events. These would extend their effects far beyond a single neighborhood. Pyroclastic flows, dense currents of hot gas, ash, and volcanic debris moving across the ground at tremendous speed could threaten communities around the caldera and potentially reach parts of Naples. Thick ashfall could blanket much of southern Italy, damaging buildings, contaminating water supplies, and disrupting transportation networks. In such circumstances, the interval between unmistakable warning signs and hazardous conditions might be measured in hours rather than weeks. Emergency planning, therefore, revolves around rapid decisions made under considerable uncertainty. Farther along the spectrum lies the event that shapes every long-term discussion of Campi Flegrei. Approximately 39,000 years ago, the Campanian Ignimbrite eruption demonstrated what this volcanic system can achieve under exceptional conditions. No scientific assessment considers a comparable eruption imminent, nor do researchers regard it as a likely outcome in the near future. Even so, the deposits surrounding the Mediterranean preserve evidence that the physical capability exists within the system. Geology records possibilities, whether they occur tomorrow or after many thousands of years. The difference between a moderate eruption and one approaching Campanian Ignimbrite scale extends beyond a matter of size. Effects do not increase in a simple step by step progression. A larger eruption influences broader regions, more infrastructure, and more interconnected systems. Transportation, communications, trade, agriculture, and energy networks become increasingly vulnerable as the scale expands. This reality explains why monitoring programs, evacuation planning, and scientific research receive sustained attention even when immediate risk assessments remain moderate. Volcanic ash alone illustrates that challenge. Fine particles carried high into the atmosphere can travel enormous distances and interfere with aircraft operations. In 2010, the eruption of Eyjafjallajökull in Iceland, classified as a volcanic explosivity index 4 event, disrupted air travel across Europe for nearly a week. Campi Flegrei occupies a far different geographic position, surrounded by some of the busiest transportation corridors in the Mediterranean. Even a moderate eruption could affect aviation, commerce, and daily life far beyond Italy. For that reason, the future of Campi Flegrei is studied not through certainty, but through preparation, observation, and an ongoing effort to understand the many paths a living volcano may take. A volcano can reveal itself through catastrophe, yet Campi Flegrei offers another lesson. It reveals itself through conversation. The language is geological rather than spoken, expressed through shifting ground, changing gases, and countless fractures deep within the crust. For centuries, people living around the caldera have witnessed fragments of that dialogue, though only recently have they gained the tools to interpret it with precision. The history of the caldera contains a pattern that stands out with unusual consistency. Major eruptions have not emerged from complete stillness. Before magma reached the surface, the landscape changed. Shorelines moved, earthquakes multiplied, gas emissions evolved, pressure accumulated gradually enough to leave traces behind. These signals did not guarantee certainty, but they provided evidence that the system was entering a different state. The eruption that formed Monte Nuovo remains one of the clearest examples. Decades before the first explosion, residents noticed the coastline behaving differently. Areas that had once been submerged began emerging from the water. By the early 16th century, those changes were visible without scientific instruments. During the years leading up to the eruption, earthquakes became more frequent and more difficult to ignore. When the eruption finally arrived in 1538, it emerged from a sequence of warning signs that had unfolded across many years. Modern unrest episodes have followed a similar rhythm, though observed through increasingly sophisticated technology. During the crises of the 20th century, instruments recorded uplift and seismic activity well before those episodes reached their peaks. Scientists tracked changes as they developed, providing authorities with information that earlier generations could never have obtained. Difficult decisions remained, yet those decisions were informed by evidence arriving in real time rather than by rumor or surprise. The current period of unrest has expanded that record dramatically. Since 2005, the caldera has been monitored continuously. Every earthquake swarm, every pulse of uplift, every shift in gas chemistry has added another layer to an exceptionally detailed archive. Nearly 2 decades of observations now provide a baseline against which new changes can be compared. A signal that might once have appeared ambiguous can be evaluated against years of previous behavior, making acceleration, deceleration, and unusual patterns easier to recognize. This characteristic separates volcanic hazards from some other natural events. Large earthquakes may occur with very limited warning, developing on timescales measured in moments. Volcanoes often operate differently. Magma moves through rock, pressure accumulates, and fractures expand. Those processes frequently generate observable clues before an eruption begins. The interval may range from years to months, weeks, or days, but the system often announces that conditions are changing. No monitoring network can eliminate uncertainty. Instruments cannot provide a precise calendar date for a future eruption, nor can they transform a complex volcanic system into something fully predictable. Campi Flegrei continues to challenge every model built to describe it. Even so, uncertainty is different from ignorance. Scientists today possess information that earlier generations lacked, and that information creates opportunities to prepare, evaluate risks, and respond. Around the caldera, thousands of sensors, researchers, emergency planners, and civil protection officials form a network dedicated to understanding a living supervolcano. The effort is imperfect, shaped by scientific debate, practical limitations, and human judgment. Yet it represents something remarkable in its own right, a sustained attempt to listen carefully to a restless landscape while it continues to speak. Across the history of Campi Flegrei, one pattern appears again and again. People arrive, build homes, raise families, create stories, wage wars, establish cities, and pass their knowledge to the next generation. The caldera remains through all of it, following rhythms so prolonged that a single human life captures only a fragment of the larger sequence. When the Great Eruption of roughly 39,000 years ago transformed the region, the people who witnessed it possessed no geological framework through which to interpret the event. Neanderthals and early modern humans knew landscapes, seasons, animals, and weather. They knew the practical realities of survival. The forces gathering beneath the ground belonged to a scale of time and process beyond direct observation. What reached them was the eruption itself, a sudden intrusion of geological power into human experience. Many thousands of years later, Greek settlers encountered a landscape already marked by fumaroles, warm springs, and ground that seemed capable of changing character without warning. Their response took the form of mythology. Lakes became gateways to the underworld. Caverns acquired spiritual significance. Stories linked visible phenomena to powerful beings dwelling below the surface. These interpretations reflected a desire to fit unusual observations into a coherent understanding of the world. Smoke rising from the earth, trembling ground, and poisonous gases demanded explanation, and mythology provided one. Roman civilization approached the same terrain from a different angle. Engineers constructed roads, harbors, villas, and military facilities. Practical ambitions shaped the landscape. At the same time, Roman literature preserved many of the older stories inherited from Greek traditions. Engineering and mythology existed side by side. A harbor could be dredged, a tunnel excavated, or a fleet assembled while legends continued to circulate through poetry and cultural memory. The volcano remained present in both worlds. Centuries later, medieval communities watched coastlines shift as the caldera floor rose. Land emerged where water had once stood. Settlements adapted to changes unfolding gradually enough to become part of daily life. Then Monte Nuovo appeared within a single week. A process that had developed over decades suddenly entered human timescales. The eruption compressed years of geological preparation into days that could be observed directly, leaving a lasting impression on those who experienced it. Modern volcanologists inherit all of these earlier observations, though filtered through instruments, measurements, and scientific models. They track earthquake swarms too small for people to feel. Satellites detect deformation measured in millimeters. Gas chemistry reveals changes occurring far below the surface. Yet, even with these tools, the caldera resists simple categorization. Data illuminate the system more clearly than ever before, while many uncertainties remain intact. Part of the challenge lies in the mismatch between geological time and human time. Major eruptions may be separated by thousands of years. Unrest episodes unfold across decades. Scientific records span generations. Human institutions, however, operate through election cycles, careers, budgets, and lifetimes. People who remember one crisis eventually leave the stage, while decisions about the next crisis fall to those who know it only through documents and memories. Campi Flegrei exists at the meeting point of these two clocks. One measures centuries and millennia, the other measures lives. Both continue together across the same landscape, each moving at its own pace, each shaping the story of the caldera in different ways. A person can stand on a balcony in Pozzuoli at sunset, watching ferries move across the bay and lights appear along the shoreline without giving a single thought to magma. Dinner is being prepared in nearby apartments. Children finish homework. Conversations drift from sports to work schedules to weekend plans. Life unfolds with the ordinary concerns that occupy people everywhere. Several kilometers below, which is about several miles below, the volcanic system continues its own long cycle, largely unnoticed through most hours of most days. That separation between daily life and geological reality is not unusual. It is one of humanity's oldest adaptations. People learn to coexist with conditions they cannot eliminate. Communities settle beside rivers that flood, coastlines visited by storms, and fault zones capable of earthquakes. Campi Flegrei belongs to that same category. The residents understand where they live. Awareness exists in the background, woven into local culture rather than dominating every moment. Occasionally, the relationship becomes more visible. A tremor rattles windows during the night. Plaster falls from an aging ceiling. Engineers inspect a cracked wall. News reports discuss the latest measurements from monitoring stations. Letters from civil protection authorities remind households to review evacuation procedures and designated routes. Conversations that normally remain dormant emerge around dinner tables and in neighborhood cafes. People compare experiences, discuss recent earthquakes, and wonder how the current unrest fits into the longer story of the caldera. The landscape itself encourages that awareness. Apartment buildings stand beside Roman ruins. Roads cross terrain, shaped by earlier eruptions. Harbors occupy coastlines that have repeatedly risen and fallen through Bradyseism. In many places, evidence of geological change exists only a short walk from evidence of human history. The same ground that supports schools, hospitals, and businesses also records centuries of volcanic motion. Past and present share the same streets. Memory contributes another layer. The story of Monte Nuovo remains part of the region's identity. During 1538, residents watched a new mountain emerge over the course of a single week. Day after day, the cone grew higher. Curiosity attracted visitors eager to witness an event unlike anything they had seen before. Near the end of the eruption, 24 people climbed the new cone after activity appeared to be fading. A final explosion ended their lives. The episode survives as a reminder that volcanic systems do not always follow the expectations people place upon them. No simple moral can be drawn from that event. Campi Flegrei does not move according to human narrative structures. Activity may accelerate, weaken, pause, and resume. A period of unrest can continue for years without an eruption. Signals that appear alarming may diminish. Other changes may prove more significant than they first seem. Scientific monitoring has advanced enormously, yet uncertainty remains part of the reality. Living here, therefore, involves a continuing negotiation between vigilance and normality. Residents cannot spend every day focused on volcanic risk, and they cannot completely forget it either. Life unfolds in the space between those positions. Shops open each morning. Families make plans for the future. The ground rises by small increments. Instruments record the changes. Human lives continue on the surface while geological processes continue below, each operating according to its own measure of time. A layer of gray volcanic rock runs through the history of southern Italy like a thread stitched across thousands of generations. It appears in cliffs, road cuts, foundations, tunnels, and ancient walls. People have quarried it, carved it, and built upon it for centuries. Few pause to consider that this stone was created during a span of hours 39,000 years ago, when Campi Flegrei produced one of the largest eruptions Europe has ever witnessed. The story begins with that eruption, yet it does not end there. Ash traveled across the continent, settling over landscapes inhabited by both Neanderthals and modern humans. Pyroclastic flows reshaped the region surrounding the caldera. A new geological chapter opened. As centuries became millennia, weather and vegetation softened the scars. New communities arrived. Paths became settlements. Settlements became cities. The deposits remained, carrying the memory of the eruption into every age that followed. Those same deposits eventually provided building material for Naples and the towns around it. The rock formed from volcanic ash proved useful for construction, easy to quarry and shape. Houses, roads, fortifications, churches, and harbors emerged from material created by the catastrophe that came before them. In a literal sense, the city grew from the products of the eruption. Human history here rests upon geological history, each layer supporting the next. The landscape also shaped imagination. Near Lake Avernus, fumes rose from the earth, and unusual geological features marked the terrain. Greek settlers and later Roman writers interpreted these places through mythology. Virgil incorporated them into stories of journeys to the underworld. More than a millennium later, Dante drew upon related traditions while constructing his own vision of the afterlife. Ideas that influenced literature across the Western world were rooted, at least in part, in observations of a volcanic landscape whose behavior seemed unlike anything else people knew. Far older than those stories were the Neanderthals who lived in Europe before the eruption. They endured changing climates through hundreds of thousands of years. They adapted to glacial advances and retreats. Then the archaeological record becomes thinner in the decades following the Campanian Ignimbrite event. Scholars continue to debate the precise role the eruption played, yet their disappearance remains one of the most poignant absences in human prehistory. No written account survives. No legend records what they witnessed. Only scattered traces remain where communities once existed. Modern humans inherited the same landscape. Greek colonies appeared along the coast. Roman engineers transformed bays into harbors. Medieval towns expanded and contracted with the changing shoreline. Today, millions of people live within reach of the caldera. Scientists monitor earthquakes in real time. Instruments track ground deformation, measured with extraordinary precision. Data streams continuously into observatories, adding new pages to a record that spans many generations. Across all of these transformations, Campi Flegrei has remained governed by the same physical processes. Magma moves, pressure accumulates and dissipates, the ground rises and falls. Human cultures assign meaning to these changes through mythology, engineering, literature, science, and planning. The caldera itself follows no cultural narrative. It continues according to geology, linking Neanderthals, Roman builders, modern researchers, and future generations within one uninterrupted story unfolding across 39,000 years in a single place. Each day begins with a new measurement. Numbers arrive from instruments scattered across the caldera, collected from stations mounted on hillsides, rooftops, and rocky outcrops. They are compared against yesterday's values, then against records stretching back years. At Rione Terra in Pozzuoli, the surface stands approximately 148 centimeters higher than it did in 2005. The change has unfolded gradually enough to escape notice in daily life, yet large enough to reshape the landscape when viewed across decades. Deep below, rock continues to adjust to pressure, producing countless tiny fractures that sensitive seismometers record one after another. Within the Vesuvius Observatory, those signals become part of a growing archive. Scientists examine fresh data alongside measurements gathered last week, last month, and last year. Patterns matter more than individual events. A single earthquake may reveal little. A cluster occurring in a particular location can suggest movement through a fracture network. A change in ground deformation may indicate that pressure is accumulating differently than before. Every observation gains meaning through comparison, turning isolated numbers into a narrative written by the volcano itself. What makes this moment unusual is not the unrest alone. Campi Flegrei has experienced unrest before. What is new is humanity's ability to observe nearly every stage of the process while it unfolds. Satellite systems track changes across the caldera with extraordinary precision. Instruments measure gases escaping from fumaroles. Gravity surveys reveal shifts in material beneath the surface. Automated seismic networks identify events too small for previous generations to detect. For the first time, a supervolcano is being watched with tools sensitive enough to register many of its smallest motions. 39,000 years ago, the Campanian Ignimbrite eruption unfolded in a world without written records, observatories, or scientific instruments. No witness left a description of the sky. No measurement captured the changing pressure within the crust. The eruption announced itself only through its consequences. Ash settled across continents. Landscapes transformed. Deposits accumulated layer upon layer, preserving evidence that would remain unread until distant descendants learned how to interpret it. Today, researchers read those ancient deposits while simultaneously monitoring the living system that produced them. Core samples recovered from the ground converse, with streams of digital information arriving every second. One record reaches backward through deep time. The other arrives from the present moment. Together, they reveal a volcano that remains active, complex, and difficult to reduce to simple rules. Whether Campi Flegrei erupts again next year, next century, or far beyond any current lifetime remains unknown. Scientific monitoring can identify accelerating change, narrowing uncertainty as events develop. It cannot erase uncertainty entirely. Nature rarely offers exact schedules. Virgil once wrote that the descent to Avernus is easy, while the journey back demands greater effort. The line endured because it reflected something people sensed in this landscape long before modern geology existed. The Earth here reveals hints of forces operating far below ordinary experience. Tonight, the ground continues its gradual rise. Instruments continue their watch. Data continues to accumulate. Across the burning fields, Deep processes that shaped continents and civilizations remain in motion, linking the distant past to the present through a story that has not yet reached its final page.